This is a lecture for section 7.8 on improper integrals. The idea with an improper integral is that infinite graphs can encompass a finite amount of area, and I'll explain this with an example. So if we look at the area under the curve, y equals e to the minus x in the range from x equals 0 to t, right? So the graph looks like this, and if the t value is here, the area under that curve is given by the integral from 0 to t of e to the minus x dx. And we can compute that rather easily. As 1 minus e to the minus t. And this is units squared. Now, the idea is that as t goes to infinity, or as t gets larger and larger, then this function, e to the minus t, gets closer and closer to 0. And so if we take the limit, so the area under the curve y equals e to the minus x in the range from 0 to infinity, we could define that as a limit. Specifically the limit of the area that we computed above. So this would be the limit as t goes to infinity of 1 minus e to the minus t, which, because the factor of e to the minus t has a limit of 0 as t goes to infinity, we get that the area is 1 unit squared. In general, we have the following formulas for what we call improper integrals of type 1. So there are 3 different cases to consider. The first of these is an integral of the form integral from a to infinity f of x dx. And this is defined to be, just like we did in the previous example, a limit as the right-hand endpoint goes to 0 of the integral from a to b, b being the right-hand endpoint, of f of x dx. If this limit exists, and furthermore, we have to assume that the limits from a to b f of x exist for all b. For instance, this last condition holds if we're integrating a continuous function, because continuous functions are always integrable. When the limit exists, we say that the integral is convergent. Otherwise, the limit is divergent, or the integral is divergent. The second case is similar to this one. I'm not going to write out all of the conditions, but it's the integral from negative infinity to b. This function, which is defined again to be the limit, this time as we let the left-hand endpoint go to negative infinity. With the same conditions as in part A. The third case is the case where we integrate from negative infinity to infinity of this function f of x. And in this case, it's defined to be the integral from negative infinity to c f of x dx plus the integral from c to infinity of that function, provided that both of those integrals are convergent. Okay. So notice that if you see an integral from negative infinity to infinity, you are required to split it up into two integrals and to treat those integrals each separately. And here the choice of c is whatever you like. Usually we'll pick something like 0 that makes things symmetric. So let me show you a quick example on the next page. For example, the integral from 1 to infinity of one over x to the fifth dx can be written as the limit as b goes to infinity of the integral from 1 to b of, let's write that 1 over x to the fifth as x to the minus 5. And this, we can take that antiderivative really easily. So the limit as b goes to infinity of x to the minus 4 divided by minus 4 evaluated from 1 to b. So we evaluated b in 1 and subtract, and we end up with 1/4 minus, let's write it this way, 1 over 4b to the fourth And as b goes to infinity, the denominator of this second expression goes to infinity, so the quotient goes to 0, and we find that this integral is 1/4. Notice that I'm not writing out units squared on this because I'm not computing an area. I'm just evaluating the integral. And so this particular one is convergent. Other examples like this can be found starting on page 520. Examples 1 through 4. Now, there's another type, right? So the integrals at infinity are the type 1 improper integrals. The type 2 are the ones where we have vertical asymptotes. So graphically, if I'm looking at a function like this, I have a vertical asymptote here, and I'm interested in finding the area, say, from A to B, where my vertical asymptote is. Well, what I can do is to find the area from A to T, where T is less than B, and then let T go to B from the left-hand side. And this is precisely the definition that we have for the indefinite integrals of type 2, which I'll show you on the next page. So there are 3 types again. The first type is like the picture that I just showed you. So f is continuous on the interval from A to B, not including B, and is discontinuous at the point x equals b. Then we would define the integral from A to B, f of x dx, to be the limit as t goes to b from the minus side of the integral from A to t, f of x dx, provided again that this limit exists. And again, we use the terminology of convergent if the limit exists and divergent if the limit does not exist. Similarly, if my discontinuity occurs on the left of the interval that I'm interested in, then my integral from A to B of this function would be the limit as t goes to the left-hand discontinuity from the positive side of the integral from t to b f of x dx. The third situation that we encounter is the situation where the vertical asymptote occurs in the middle of the interval. So if f of x is continuous on the interval from A to C and on the interval from C to B, then the integral from A to B f of x dx is defined to be the integral from A to C f of x dx, which is a limit, and that's a limit that has the same type as type A, plus the integral from C to B, where the discontinuity is now on the left, f of x dx. So this one is another limit. And just like in the case where we integrated from negative infinity to infinity, this limit is only said, this integral is only said to be convergent if both of those integrals are convergent. So let me show you an example of this on the next page. So I'm interested in evaluating the integral from 6 to 8 of 4 over x minus 6 quantity cubed dx. Notice that we have a discontinuity for our function at x equals 6. And in case you've forgotten about discontinuities, the primary thing to worry about is whether or not you've divided by 0, or whether or not you've tried to take the square root of a negative number. So the way that we would evaluate this, since the discontinuity occurs on the left, so this is type B from the previous slide, previous page, we would write this as a limit as t goes to 6 from the positive side of the integral from t to 8, 4 over x minus 6 cubed dx. Now that integral is one that's relatively straightforward for us to compute. So x minus 6 cubed is x minus 6 to the minus 1/3. So we have 4 times x minus 6 to the minus 2 over minus 2, and then we evaluate from t to 8. Again, so let's see here, the 4 and the minus 2 cancel, and when we plug in 8 and t, what we get, let's simplify, we end up with negative 2 times 1/4 minus 1 over t minus 6 quantity squared. Oops, I forgot my limit here, so let's fix that. Like this. Now, as t goes to 6 from the positive side, here I'm dividing by something that's getting closer and closer to 0. And so this is going to positive infinity as t goes to 6 from the positive side. This is not a finite number, so in this situation, this integral is divergent. So whenever you have one of these situations, if your limit ends up being plus infinity or minus infinity, you have to be very careful about that. That's going to give you a divergent integral. The other thing that this raises is now whenever we have an integral, we have to worry about whether or not we've been given an integral that has a discontinuity in it. Okay. The last topic to talk about in this section is comparison test for improper integrals. And the comparison test works like this. You have two functions, f and g, where f is greater than or equal to g, and g is non-negative. And what you're interested in is you're interested in understanding the convergence behavior of the integrals from a to infinity of these functions. And there are two situations where you can draw conclusions. So in the situation where the larger of the two functions converges, this is saying that this integral that we have is a finite number because we're integrating a non-negative function. And because this f of x function is greater than or equal to the g of x function, if the integral of the larger function is finite, then the integral of the second function has to be finite as well. And that's the conclusion here in the comparison test. Part B is if the smaller function has a divergent integral, then so does the larger one. And the logic here is similar. If the smaller function has an infinite integral, that is an infinite area, then the larger function has to have infinite area as well, because the area has to be larger. Okay? So I'm going to finish the lecture here in the interest of time. You should look at examples 9 through 10 in the book for more about this. And what you're going to have to do in order to apply the comparison test properly is you're going to have to keep some specific examples in mind. So the examples to keep in mind are that the integral from 1 to infinity of 1 over x dx diverges, and this is example number 1 in the book. Example number 4 in the book talks about the integral from 1 to infinity of anything of the form 1 over x to the p dx. Here p is some number, and this converges whenever p is greater than 1, and it diverges whenever p is less than or equal to 1. Okay. And the third example is the first one that we did earlier, that the integral from 0 to infinity of e to the minus x dx also converges. And I think I forgot to point out in the previous page that the type 2 indefinite integral examples in the text are examples 5 through 8. Okay, so that's the end of the lecture on section 7.8, improper integrals.